Okay, welcome to lecture 9.3. Um, all right, here's what we're going to do. Now we're going to start thinking about how to estimate lambda. By the way, the McKelvey-Palfrey model, there's only one parameter to estimate, and that's lambda. Okay. Here's what we had. So now we're in the ox model, okay, like the matching pennies game. And we had two equations, two unknowns, okay? Sigma A, which we want that to equal PA, A1. With sigma B, B1, we want that to equal PB, B1, okay? So we've got to find PA, A1, PB, B1 to make that equation true. So the idea is to think about it as if we are the equilibrium God, and we've got to announce a correct PA, A1, PB, B1. Okay. First case, let's think of the simplest case possible. What if I told you that lambda equals 0? Okay. What would be the value of P, AA1, and AA2 that would make these equations true? Okay. Well, first of all, if we did that, if lambda equals 0, okay, then what we have here in the numerator is just e to the 0. That's 1. What's that number? E to the 0. That's going to be 1. What's that number? E to the 0. That's going to be 1. So it's going to be 1 over 1 plus 1. Okay. So that means that PAA1 has to equal 1/2. Okay. Same thing here. What if lambda equals 0? That's going to be 1. That's going to be 1. That's going to be 1. The value that works, PBB1, just has to equal 1 over 1 plus 1, or 2. Okay. So if lambda equals 0, it's easy. The only values that work are going to be set the two values of P equal to 1/2. Okay. Okay, that's the first situation. Okay, we've got let's see, and here's what we're trying to do. Here's what eventually we're going to need is we're going to need. So let's call this. By the way, let's call it PA A1 star. Okay, I'm not going to write it, but that equals the P and PB B1 star. Those are the two values of PA, the P's that make these two equations true. Okay. Now, what I should have done is these depend on lambda. For different values of lambda, we're going to get different values of P, A1, BP, B1 star. Okay. All right. What we want to do now is start thinking about a table. Okay. So we're going to have lambda, PA, A1 star, and PB, B1 star. Okay, and I didn't write it, but remember these are functions of lambda. So we've already done this. If lambda equals 0, the PA A1 star has to equal 1/2. And same thing for P B1 star. Okay. All right. What we want is a big table for all the different possible values of lambda. And for your homework, you're going to do this. So when lambda equals 0.0, and maybe I should have done this in thousands rather than hundreds. Okay, you do this. So we're going to substitute, instead of 0, we're going to substitute lambda equals 0.01, find the PA, A star, and so on. Okay, now I'm not going to do that, but I'm going to do one. I'm going to say What about P lambda when lambda equals 0.2? Okay. Let's try to find the P stars when lambda equals 0.2. How do we do that? Okay. So what I've done is I've got this spreadsheet, and here, let's see, so you can see me. Okay, I'll be in the background here. What I've done, so see, I've started off, okay, and I filled in this table, PA1, by the way, so I've just put in, these are like seed values, okay, so PA, B1, I've put in 0.5 for the moment, okay, I have different values of lambda that we can try. First of all, let's put in lambda equals 0, make sure, darn it, is that right? Oh my gosh. I have got an error in this. Expo C2, 1 minus A2. Oh, I see it. Does that work? Darn it. Okay, I think it corrected it. It got the right expo. Darn it. C plus 1 expo. Okay, I think I got it. Okay, sorry. I thought I had this right ready. Okay, so let me explain how I've done this spreadsheet. Okay, first, okay, all I've done is just typed in these formulas. Okay, so if we're given PA A1, PB B2, we can write sigma A A1. Okay, it's just this term, e to that divided by e to the blah blah blah. Okay, so let's look at this. Sigma A1 should be expa times the numerator, C2, that's lambda, times B2. That is P B1, 4 times P B1. Yeah, that's B2. Okay, 4. And then the denominator is same term, x plus C2, 4 times B2. Okay, 4 times, that's the P sub B sub B1, plus x the lambda, C2, plus 1 minus B2. I recall that's that one. Okay, so that is sigma A1. All right, sigma B1 should be this formula, which is expa to the C2, that's lambda, times 1 minus A2, so that's 1 minus P A sub 1, okay, got that. Okay, all divided by expa, that same term, plus expa C times A2, expa P times A1, okay. So I should have, let's assume I've typed that correctly, that formula. Okay, so it works. So I just said, we did it by hand when lambda equals 0. All right, now let's try it when lambda equals 0.2. All right, so I've changed it to 0.2. All right, what happens? Darn it. No, I think that's right. I was thinking sigma B1 would be wrong, but I think I got it right. Okay. Now, the problem is what we want, remember, for an equilibrium, we have to specify a PAA1 and a PBB1, and the sigmas have to equal the P's, and we don't have that. Sigma AA1 does not equal PAA1. Okay. All right. Now, one thing we could do is we just start trying 0.5742. Let's see what happens. Um, okay. So we get closer. A1 equals sigma A1, but now B1 is not quite right. So, to what? Let's try B1. Let's do 0.4992. Let's see if that, what happens. Okay. Yeah, we're getting closer. 0.4925 should be sigma B1. Sigma A1 is 0.5724. Okay, didn't quite get it right. Here is a trick I'm going to do. Okay, so now notice that sigma A1, so all it used was PB1. Sorry, yeah, so which is in cell B2. Okay, notice it didn't use the A cell A2. Okay, meanwhile sigma B1, it used cell A2. Okay, now we want this PA1 equal to sigma AA1. Okay, now it turns out that sigma A1 doesn't even use that cell A2. So you know what I'm going to do? I'm just going to, here's a little trick. I'm going to set that A2 just equal the sigma AA1. Okay, since sigma AA1 does not use PAA1, I can do that. This isn't like a self-referential definition in this case. So all I'm going to do, I'm going to set that cell equal to sigma AA1. So this is a little shortcut. Okay, once we've done that, all I got to do is find the PB1 that makes PB1 equal to sigma BB1. Okay, so I'm pretty close. 0.492. Let's try 0.49275. Let's see what happens. 0.49275. What happens? Okay, that changed that to 0.49273. So let's change PB1. Try it again to 0.49273. See what happens. Okay, got close enough. Okay, so let's suppose that we found the equilibrium. I have found the sets of P A1, P so B1 that form an equilibrium, and that's for the lambda equals 0.2. So what we would do is we would just get our table, and we'd say, well, when lambda equals 0.2, the PAA1 star equals 0.5726. Close enough. 0.66 actually. PB1 star is going to be 0.4927. 0.4927. Okay. All right. Now, to estimate lambda star, okay, to do the maximum likelihood estimation, first thing you got to do is complete that table. Okay, you got to look for all the lambdas. Try all the lambdas, 0.0, 0.01, 0.02, so on. Okay, fill out that table. Now lambda could be anything from 0 to infinity, so it's going to take a long time. At some point, you can't be quite as precise in the difference from one lambda to the next, but hopefully you get the idea what you would kind of have to do to create a table. All right, now here's what you would do next when estimating lambda. Okay, next thing you do is get your data. Okay, now let's assume Okay, suppose, let's see. Okay, now our data is going to be, it's going to specify the two actions that the two players took. So it's, so let's, okay, suppose data are the following. So we have, let's suppose we have three observations, 1, 2, 3, and y1. And instead of a number, what I'm going to do is I'm just represent it as the actions. Okay, let's say it was A1, B1. Okay, in observation 2, let's say it is A2, B1, and Y3 equals A1, B2. Okay, so that is, suppose that you've run this experiment 3 times. And in the first case, player A did action A1, player B did action B1. In the second case, in the experiment, player A did A2, player B did B1. Third case, player A did A1, B did B2. How did I do it? Yeah, okay. All right, so that's the data. All right. Now, what does the likelihood function look like? Well, it is a function of one parameter, L, okay, and it equals what's the probability that we see the first observation? A plays A1, B plays B1, okay? It's just P, A, A1, and now we're looking for an equilibrium, star, and it's a function of the lambda. So we can pretend like we know the lambda. Okay, we're going to estimate it, but pretend like we know the lambda. The probability of observing that, and by the way, we'll assume that the two players are their error terms are independent, so their probabilities are independent. So the probability of observing that first observation is A star, times B B1 star of lambda times, okay, that's the probability of observing the first observation. The probability of observing the second observation is A2. And you know what? I should have written that. Here's what I'm going to do. It's P A. You know what? Here's what I'll do. It should be PA A2 of lambda, but we're not writing that. We're just going to write one PA and assume and assert or define that the other PA is just 1 minus that. So we're not even talking about PAA2. We're just using, instead, let's just use P1 minus PAA1. Okay. So, so I'm going to erase that. Oh, sorry, my wrist is actually hurting. Let me take a break before I make the fourth video. So it's times 1 minus PA1 star of lambda. Let's do brackets. Times B1 star of lambda times A1 star of lambda times PBB2, but we're assuming that is just 1 minus PBB1, right? So 1 minus PBB1 star of lambda. Okay, now, so we've written the likelihood function. Excuse me. How would we estimate this? How would we estimate lambda from this? Well, we could do it a bunch of different ways. One is just trial and error. We could start trying different values of lambda. We could say, okay, let's try lambda equals 0.01, okay? Well, what we'd have to do is get our table, and we would have to look up PA1. Let me get the table. For lambda 0.01, PAA star for lambda equals 0.01. And then we need PB1 star for lambda equals 0.01. We would substitute whatever those values are. We would substitute those here and here. Then we would do 1 minus PA1 lambda. Look up on the table again. Do the same thing. PB1. Do it again. PAA1 lambda times 1 minus PB1 lambda. We just look it up on the table. And that's for lambda equals 1. Once we've done that, we can compute lambda of 0.01. Okay, that's going to be some value. Then we can do the exact same thing again for lambda equals 0.02. Or excuse me, L when lambda equals 0.02. Do the same thing, L equals lambda 0.03. Just keep on doing that over and over and over. And then find the lambda that maximizes this. That's our maximum likelihood estimate. We've done it. Once we've done that, that gives us the estimate of lambda. And if you look in the Palfrey-McKelvey paper, they do that. They list the results for the ox experiment, okay, what we've just shown, and what Palfrey-McKelvey do. So they talk about grouping these different trials. So Ox did something like 100 trials, and then Palfrey and McKelvey said, what if we put these in different groups? Like the first group is the first 20 trials, the second group is the second 20 trials, and so on. But for first, when they said for all data, that is when they didn't group it, like I just said, they found that the maximum likelihood value of lambda equals 2.656. Okay, so that's the estimate. But then they try it again, where they group it, where they estimate a different lambda for the different groups. And so I told you 20 rounds. Actually, now I look at my notes, it's 16. So they said, okay, let's look at the first 16 rounds. What's the best estimate of lambda to describe the data for just those rounds? And the answer is lambda hat equals 1.856. Okay, now they list it for the second group of 16, third group of 16. Perhaps what's interesting, they said, what about the last 16 group? So the last group of trials, last 16 trials, what's the best estimate of lambda? The answer is infinity. Lambda equals infinity is the best estimate. Okay, so that is an estimate of how, or that is a description of how they estimate lambda. The final thing I want to say about this, let's see, McKelvey-Palfrey talk about lambda being a description of the degree of rationality of the subjects. And so, as I said, so if lambda equals 0, that's like the subjects are just choosing completely randomly. They're not even looking at the payoffs at all. So it's completely random in the ox game. They're both are going to pick A1 or A2 with probably 1/2, B1, B2 with probably 1/2. That's when lambda equals 0. When lambda equals infinity, that's when they're perfectly right. We can call it perfectly rational, and they're basing their decision completely by the money payoffs, and they're behaving exactly like Nash predicts in the mixed strategy equilibrium. And so that I can't remember. I think PA1 was 0.2, something like that, and the other one mixes 50. One of them mixes 20%, 80%, and the other mixes 50%, 50%. So that's what the Nash mixed strategy equilibrium predicts. If lambda equals infinity, that's what you'll get. Okay, so so I guess the best estimate of how the players acted, at least in the last 16 rounds, they acted. The best estimate of lambda is that they acted something like Nash would predict. But all the other rounds, it was something in between completely random and exactly perfectly rationality as Nash would predict. Now, the other thing, one last point, I want to talk about this. If you read this, you'll notice that McKelvey and Palfrey, they say that they convert all the payoffs to, I think it was 1991, and I think I have this right, they convert it to 1991 pennies. Okay, so just like when you have an inflation index in macro, you talk about converting to a base year. Well, they usually have the indexes in dollars. Okay, so what McKelvey and Palfrey have done, they've looked up the inflation tables, converted it to 1991 as the base year, and then multiplied it by 100 to convert dollars into pennies. Now, they wanted to do this. They converted all of the payoffs into the same units, okay, the same base year and the same currency, pennies. The reason why, and I talked to Tom Palfrey about this, and he told me that they thought that they might be able to discover something like a universal constant. So just like in physics, so we usually say, label c as the speed of light. I think I have this right, 186,000 miles per second. So that is one of the universal constants in physics. C equals 186,000 miles per second. And there's other universal constants like big G, the Newton's gravitational constant. I have no idea what that number is, and I'm sure it's units either, but it's some number, and physicists have discovered it, and it's the same throughout the universe. Same with the speed of light. And McKelvey and Palfrey thought that this lambda might be the same across all experiments, that it was going to be a universal constant within social science. And Tom Palfrey told me, he said, we looked at a few experiments and it didn't work. So we gave up on that. But they started off thinking that, and that's why they always converted the payoffs into the same currency and base year, 1991 pennies. Okay, so a little anecdote on that. Okay, so that's a little taste of it. You should have an idea of what a quantal response equilibrium is, and also you should have a pretty good idea of what's going on with the McKelvey-Palfrey model, how they use maximum likelihood estimation to estimate the lambda for these various games. Okay, so I will end there and talk a little bit more in lecture 5.4. See you there.